Okay, so we're on vaping problem number 2 and steady state matrix problem. And so we have the same scenario, except we're not told how many the group is in the group of vapors and non-vapors, but this is the matrix that allows us to go between vaping and still vaping and not vaping and so on and so forth. And if we look even here, before we had a steady, an initial state matrix of 7842. But now we're in 2793. And when we had the 7842, my steady state matrix ended up being 40 and 80. Let's consider what happens when I do 27 and 93. And so for A part, I want my S matrix. I'm going to go T to some big number of S0, where n goes to infinity. And so I'm going to go T to the n of 27 and 93. And so now you can see I have A in here and B is as such. I'm going to go matrix A to the power of, I know I can go up to 70, and matrix B. When I do that, I get 40 and 80. Peculiar. When I do B now, I'm going to go, S is going to be T to the N, S sub 0, and N is going to go to infinity. I'm going to go T to the N, where my S sub 0, though, is 119. So in total, these added up to 120, and these added up to 120. And I have a feeling, well, let's see what happens when I do that. My C matrix, I believe C is 119, and so let's go to matrix A to the power of 70 times matrix C. And when I do that again, I get 80. So even when I was really extreme 1 and 119, my steady state matrix, or my steady state vector, is 40, 80. This was a total 120. This is also 120. And so my steady state is the same. Well, let's try a totally random vector. Let's do it again. But my vector here, let's try 12, 12. This is not adding up to 120, and these are exactly equal. And as n gets large, S, well, if we do that, I think I've put it into matrix D. I have. So if I go matrix A to the power of 70 times matrix D, I get 8 and 16. 8 and 16. Now if I do D, my long-term probability matrix, to the n as n goes to infinity, when I do that, let's just take a look at matrix A to the power of 70. And I end up with, this is equal to 1/3, 2/3, 1/3, 2/3, 1/3, 2/3, 1/3, 2/3. Well, this is quite interesting. Now, it says, what conclusion can be made about the initial state vector S0 and S? Well, what I notice is that these all came out the same, no matter what my initial matrix was. These were the same. This one was not the same, but if I consider it, I know the total was 120, and this is 1/3 of 120, and this is 2/3 of 120. 1/3 and 2/3, and this is 24. Well, this is 1/3 of 24, and this is 2/3 of 24. So what conclusion can be made with the initial state vector and S? Well, it doesn't matter what my initial state vector was. Here's my initial state. It doesn't matter what it starts at. I know that S will always end up in the proportion of the long-term probability matrix. Okay, and so it doesn't, so S sub 0 does not matter. Doesn't matter. S will always end up in the proportion of t to the n when n is large, no matter what. And that's pretty interesting that that happens, what it does.